Now that we've discussed Hermitian matrices, we're going to discuss a decomposition made possible by them. This is the sure decomposition. With this, if we have a matrix A that is an n by n square matrix, it could have complex entries. This is the general sure decomposition lemma. Then we can write A is equal to Q lambda Q Hermitian. And Q has some special properties. It's unitary, which means that QH is equal to Q inverse. And also, lambda is an upper triangular matrix. Now this works for any square matrix A, complex or real. So the first property to come out of this, we won't prove it, but we'll state it. That is, since lambda is similar to A, it has the same eigenvalues. And since it's upper triangular, these eigenvalues are the diagonal elements of lambda. Okay, so this is the sure decomposition. Now let's look at what happens when we have Hermitian matrices. If we have Hermitian A, then let's go ahead and write its sure decomposition, Q lambda Q Hermitian. And we know, because that's equal to A, and A is Hermitian, that we can take the Hermitian of both sides. And thus, using the same properties that we used before, we get Q lambda H QH. Well, since lambda H is equal to lambda, then we know that lambda must be diagonal. And not only that, it must be real. Okay, so that's a beautiful property. Let's go ahead and look at what Q is. How do we find Q for Hermitian matrices? Go ahead and start the way we did before. A is equal to Q lambda QH. Since Q is unitary, if we multiply the right side by Q of both sides, we're going to get A times Q is equal to Q times lambda, and then the QHQ cancel. And that's what we've got. So let's go ahead and rewrite this in terms of the columns of Q so we can see what's going on in here. And we'll define Q is equal to the matrix made up of columns Q1 through Qn, little q1 through little qn. Then A times Q will be A times each column of Q, respectively, and that will make up the columns of the product. But since on the right-hand side, we know that Q it's equal to Q times lambda, which is a diagonal matrix, we get lambda 1, Q1, lambda 2, Q2, and so on and so forth. And from here, it's very clear that what we have, in fact, I guess we should probably define where those lambdas came from. We're going to define our capital lambda as equal to the diagonal matrix of lowercase lambda 1 through lambda n. Okay, well, we've seen this property before. This implies that the columns of Q are, in fact, the eigenvectors of A. Put a big red box about that. Okay, well, now that we know that the QIs are the eigenvectors, we're going to switch back to the notation we used on the previous page, where we used U for the eigenvectors. Sometimes we'll use V's, but this will keep it a little bit straighter. So now, using this notation, we're going to create a matrix of eigenvectors. There we go. And from the properties that we've had above, the fact that this is unitary, we know that for a Hermitian matrix, actually, let's back up. We know because of the Schur decomposition that Q is unitary. Therefore, our U matrix is unitary. Therefore, Ui Hermitian times Uj is going to be 0 whenever I does not equal j. And as we discussed previously, and is implied here, we can always have the eigenvectors normalized so that the magnitude of ui squared is equal to 1. In other words, ui Hermitian times ui is equal to 1. Now we have everything we need. In fact, we've kind of got it, but let's put it all together here. That is that the spectral decomposition of A is given by A equal to U lambda UH, where lambda is the diagonal matrix containing the eigenvalues of A, U contains the corresponding eigenvectors, and that's it. I want to say one more thing, though, about this idea of spectral decomposition. Usually in signal processing, when someone talks about spectrum, we're thinking Fourier spectrum. And this is more general than that, but it actually does include the Fourier representation of certain types of matrices. For example, if U were made up of, and we'll talk about this more later, but just as a peek under the hood, if U were made up of the basis functions of the DFT, and A was a circulant matrix, then this would actually be performing the Fourier transform, giving us the Fourier transform coefficients and then going back into the time domain. We'll talk about that later. So it does actually give us spectral decomposition in the traditional sense, but this is much more broad than that. And it will be very useful in analyzing later what we do with adaptive filter algorithms.